things about test taking. Therefore, if you even didn't know the question and it got to the end, circling an answer because it wasn't going to count against you would have probably been a good thing. I mean, that gives you a 1 in 4 or a 1 in 5 chance of circling the right answer. I did have somebody that left most of the test blank. So you can't get any credit if you leave it blank. Number 2, if you have a multiple choice test or a true false test and you circle the answer, unless you positively know that you have circled the wrong answer, do not change your answer. On one of my tests in another class, it cost somebody 25 points because they had circled the right answer at one point and had erased it and circled the wrong answer. I can tell you on problem number 2, there were more than one of you who had circled the correct answer and then proceeded to circle the wrong answer. And number 2 had no extra credit on it, or no partial credit. It was a get it or not get it. So so that's one of the things. So on a multiple choice test, you don't, unless somebody has told you that there's a penalty for getting the answer wrong, which there aren't a penalty for getting the answer wrong on mine, you might as well circle and see if you can get partial credit. So that's where that comes into play. So let's kind of walk through the test. So the first one was if you drove day and night without stopping for a year, what would be the maximum number of miles that you could drive? Of course, this meant that you had to pick a reasonable speed limit. 80 miles an hour is not a reasonable speed limit in the United States. I used 65. The text could have probably have used 55, but if you do 65 miles per hour, there are 365 days per year. And there are 24 hours to a day. And if you do that calculation, you get about 600,000. So the closest answer was 500,000. So that was that particular one. The next one was you were given that z was equal to mass times velocity divided by time. So that would be kilograms, meters per second, divided by time. Kilograms, meters per second squared. The answer was B. And again, more than one of you had the right answer and proceeded to erase it and change it to the wrong answer. All right, number 3, you were given that you were located at an initial spot of 25 meters. That was extraneous information. You had a velocity, the initial velocity was 15 meters per second, and you were accelerating at 1.5 meters per second squared, and we wanted to know what the velocity was at t was equal to 5 seconds. Velocity final equals velocity initial plus acceleration times time, 15 meters per second plus 1.5, and this is meters per second squared times 5 seconds, is going to give you, when you plug that in, 22.5 meters per second. Okay, first error in the test was as follows. This one was problem number 4. All the answers were given as an acceleration. You can tell that this question lets you calculate a couple of different things. So we are traveling along so we got a car traveling along a straight line. We start out at 30 meters per second. And we end up at 50 meters per second, and the distance traveled was 180 meters. So if you want to know the time elapsed, first thing you would need to know is the acceleration. So v squared is equal to v initial squared plus 2a times my change in position. I can solve for a, which gives me v final squared minus v initial squared divided by 2 times my change in position, which gives me 50 squared minus 30 squared divided by 360 is going to give me 4.44 meters per second squared. If you did and circled the 4.44 meters per second squared, you got half credit, because you had to get the acceleration first. Then you can do 100, or you can do distance is equal to v initial times time plus 1/2 at squared. And if you put in numbers, you get 180, 30 times time plus 1/2 my 4.44 t squared. Use the quadratic equation and t becomes minus or plus 30 plus or minus the square root of 30 squared minus 4 minus 2.22, 180 divided by 360. If you plug all that in and you take the corresponding one, it ends up being like 0.222 seconds if I plugged it into my calculator correctly. So half credit was to get the acceleration. If you drew the picture, wrote down equations, you generally would get at least a point. Okay, the next one was you were at a car traveling and you were given various times and increments. So the first one is it travels for 10 minutes at a constant velocity of 20 meters per second. So 10 minutes is going to equal 60 seconds at 20 meters per second. Gives you an initial distance of 12,000 meters. Then we're going to pass a car, so velocity final is equal to velocity initial plus AT. And our initial velocity was 20 meters per second. We went 0.2 meters per second squared times 10 seconds. Gives me a new velocity of 22 meters per second. The distance traveled then is the initial velocity times time plus 1/2 AT squared, which is 20 times 10 plus 1/2 0.2 times 10 squared. Gives me 210 meters. And then we travel 5 minutes at the 22 meters per second. And that's 5 times 60. Gives me, that's not 60, that's 600 seconds. Gives me 300 seconds. And that gives me a distance of 6,600. And so I get 12,000 plus 6,600 plus 210 gives me 18,810, or about 18,800. Most people just did partial of it, and that's where points were lost. Number 6 was, we're in charge of the New Year's Eve ball drop. And we're going to drop a ball to hit a target. So you've got your big target, and it's going to take 60 seconds. But we have to drop a ball to set the trigger. And we're told that this height is 12 meters. That our initial velocity is equal to 0. So we want to figure out the time that it takes to fall. So the easiest way to do it is v squared is equal to v naught squared plus 2a times the change in height. that was 0. So now I get V final squared divided by 2 times gravity. Square root, no, hang on. I want final height. Or V final is equal to square root of 2GH. And that gives you 15.3 meters per second. The time that it falls is V final is equal to V initial minus gravity times time. That's 0. This is going downward, so I get a negative 15.3 divided by 9.8. Gives me a time of 1.56 seconds. I have to add the 60 seconds. So it gives me 61.56 seconds. A lot of people got the 1.56 seconds, but forgot to add the 60. Okay, this problem is the toy rocket problem is the first problem that turns out not to have been as nice as it should have been. So basically what we have is a little toy rocket that's going straight up, and it's going at 2 meters per second squared for 2 seconds. Once it gets that distance, then there's no acceleration, and it's just going to do this kind of thing to it. So the intent of the problem was that, so we were disregarding any air resistance, and what we wanted to find was this height right there. That's really what we wanted to find. So the first part of the problem is you've got to do the height associated with this acceleration. So we're starting at V naught is equal to 0, and when we get to a V final, and so we need that distance first. We're also going to need this V final as well. So I did V final squared is equal to V initial squared plus 2AH. V final you had to do is V final is equal to V initial plus A times T. So this gives me that I'm going up 2 meters per second squared for 2 seconds. Gives me 4 meters per second. So now, if I'm looking at this little distance there, I take my 4 meters per second, and that gives me 16 meters per second, meters squared per second squared, is equal to 2 times gravity times the height. Okay, so I'm going to get my 16 divided by 2 times gravity gives me a height of 0.816 meters. So that's that little start up there. Then once it leaves, we can go back to this equation again, except now we get that that's 0, and that's 4 meters per second squared minus 2GH. I get 16 again, divided by 2G is going to give me another 0.816, and then you would add those two together. That does not give you any of the answers that are given. So that is incorrect. I gave partial credit for starting the problem and working through part of the problem. So this was one of the first problems that just wasn't as clean as it should have been. Hence the extra points for everybody. The next one was the two vectors. You were given vector A is equal to 5I plus 6J, and you're given vector B, which is minus 3I plus 2J, and you wanted to do 3A minus B. And so that gives me 15I plus 18J. Minus B gives me a plus 3I minus 2J. This gives me 18I plus 16J. So that's the square root of 18 squared plus 16 squared. And when you do that, you get a bizarre number. It's like 14 or 24 or something. Square root of 18 squared plus 16 squared gives you right at 24, which again was not the right answer, but most people went ahead and circled 23.3 if you got that far. So was that problem, because it was close enough. Okay, the next one, lots of people got half credit. You were given a vector that was, the vector A was equal to minus 2.5I minus 10.2J. So the arc tangent of the angle is going to be equal, or it's going to be minus 10.2 divided by minus 2.5. And when you do that, you put it in the calculator, you get 76.22 degrees. If you circled that, you got half credit. This vector is over in that quadrant. That angle is this angle right here. The angle it asked for was this angle. So you take 180 degrees minus the 76.22, and that gives you the 103.78 degrees. And that's the answer. If you gave me this angle, you got half credit. So you got half credit for that one. You got half credit for that one. This one happens to be, the 76.22 is C. This happens to be answer A, is the big one. All right, the next one happens to be the longest problem on the whole test. So when you're doing your test and you get to these and you realize this is going to take a little bit of time, you should go ahead and skip and do the rest of them, because you'll notice that problem number 14 was like a gimme. So and problem 11 was also pretty quick and easy, but problem 10 was a little hard. So what we had is we have a ball that's thrown horizontally from the top of the building. Okay, so it's thrown horizontally from the top of the building, and it lands 65 meters away from below the point of release. So it lands 65 meters away, and we're told that it's a 0.1 kilogram high building, so it's 100 meters, or kilometer building, so it's 100 meters. And we want to know the velocity when it hits the ground. Now, the velocity in the x direction times time is going to equal the distance. So the velocity in the x direction is going to be the distance divided by the time, except we don't know time. The second part of this is that we know that distance is going to equal the velocity in the y direction times time, initial velocity in the y direction, minus 1/2 gravity times time squared. That starts out at 0 because there was no y velocity initially, so I get 2 times my height divided by gravity is going to give me t squared. And so my time is going to be the square root of 2d divided by a, which ends up being 4.52 seconds. So I can take that now and I can get to my 65 divided by my 4.52 seconds. This gives me 14.3 meters per second, but that's only in the x direction. I got to find y. Velocity in the y is equal to minus gt, because it started with a 0. And so now if I have the velocity in the y direction, I get minus 9.8 times my time, because this is going to be going down, 4.52. If I punch that in the calculator, times 4.52, tells me this is 44.3 meters per second. So velocity is going to end up being 14.3 meters per second in the I direction minus 44.3 meters per second in the J direction. And so I can do the magnitude, and that's the square root of 14.3 squared plus 44.3 squared. And that gives you something that's closer to 47 meters per second. The next one, you were just trying to calculate the y component of the velocity. You were given this, that I had 22.5 meters per second. The angle was 26.5. Vy is 22.5 sine of 26.5, and that was 10.00 or 10.04 meters per second. We had a ball roll off the top and fall, and we wanted to know how far it goes from the edge. Now this is the part that always puzzles me. This is also why you can use the test to help you figure out the rest of the test. This is exactly like the lab, and it's pretty darn close to the problem above. So you can actually use this one to help you figure out how to do the problem above. So distance is equal to 1/2 AT squared. We solve for time. Time ends up being 0.49 seconds. And then, we're given the velocity is 3 meters per second. 0.49 seconds gives me 1.48 meters. If you showed your work and had circled 0.49, you got partial credit. If you showed your work. I had a lot of people just circle 0.49 and didn't show their work. And if I don't see the logic behind circling it, I'm not going to give partial credit for it. Okay, so then comes problem 13. I don't know when I wrote the question, it was supposed to be pretty straightforward. Because basically it was just a simple projectile motion problem. You were given that we had a velocity of 15 meters per second at an angle of 15 degrees. And you wanted the total time of flight when it hits. But I can't tell you where those numbers came from for the answers. Because when I went and redid this, I went, okay, not quite sure what's going on here. Because if I do this, I get Vx is equal to 15 cosine of 15 degrees. I get Vy is equal to 15 sine 15 degrees. This ends up being 3.88. If you do the V final is equal to V initial minus gravity times time, where this is, there it is. This becomes my 3.88 minus gravity times time, and that's 0. This ends up giving you time of something pretty small, 0.396 seconds. And since that's the time at the top, I have to multiply by that 2. So it's 2 time for total time of flight. And that gives me 0.792 seconds. Which is not any of the answers that are there.
Do you have an answer sheet with these? Do you have an answer sheet with this test? Or
I made up the answers.
so you're finding the answers on your own?
Yeah. No, some of these questions might have been taken from a test pool, but most of them weren't. So again, I don't know where I got the answers that I put with them. Have no idea. So that one is that particular one. The next one is a ball is tossed. It leaves the hand. It goes up. The acceleration is negative 9.81 meters per second squared. It was a gimme. You got half credit if you circled 9.81. But that one was just a straight gimme. And then this last one, you kind of had to read my mind. So there are two correct answers. The intent was a projectile motion problem and finding the height at the center of the arc. Okay? The intent was that right there. And if you did that, if it cleared just, what was the velocity of the softball in the y direction when it occurred at this point, that would be 0. So it was intended to do it just by inspection. But because if you could be looking at a variety of different angles that have it clear the fence, depending on my initial velocities, you could have had a bunch. I went ahead and also accepted you weren't given enough information. The intent was to be able to do it by inspection, but the way I worded the question, it wasn't clear. So now you know why I gave some points, because there were some places in the test that I wasn't happy with. Which is why on engineering tests and physics tests, when you get into your upper division courses, even if you're doing multiple choice and the answer's not there, show your work, because a lot of times some of us screw up. And we're looking, and I will tell you historically in physics, on your graduate entrance exams, it is not uncommon to have an unsolved problem be one of the problems, and they're looking for your train of thought, not whether or not you actually get the right answer. That happened to happen to Maxwell, and that's when he actually proved and solved the problem, which was kind of disgusting, but it happens. Sure, there we go. All right, so the other thing I have done is, because there has been a problem, and I don't know if it is a Blackboard problem, I don't know if it is a WebAssign problem, and it also occurred apparently in Connect in one of my other classes as well. Recognized that for some reason that the time, if you look, just glanced at your time stamp of when your homework was due, it looked like, and in one case I know it was Greenwich Mean Time, okay, because we saw it over there, over in Enid, and it was Greenwich Mean Time. So 1:30 p.m. Greenwich Mean Time is like 17:30, which is like 5 p.m., but if it's in GMT, 1:30 GMT is, or 17:30 GMT is 1:30 our time. There has been a revert, and in a couple of the different programs, that rather than on Central Time, they're on System Time, which is Eastern Time. So homework that was due at 11, it was counting it as being incorrect. Or it was homework that was due midnight our time, it was saying it was due at 11 their time, and we're counting them as being late. So what I decided to do in order to deal with that is that the pre-work, since it just kind of happened over this last week, that the pre-work that was due on Friday, I have extended it till Wednesday. So if you didn't get it done, or you didn't finish it, or something along that line, that pre-work for this chapter is now due on Wednesday. I did not change the homework for Friday, because we have just about gotten all through chapter 5. But there's two things I want to do today to help you out. One is to show you friction, because the lab is going to cover friction, and we really won't get that till Wednesday, because we're going to start chapter 6 on Wednesday. And the other one is looking at called Atwood problems or pulley problems. And I want you to be able to see that so that we've got that, so that you guys can get your homework kind of done. And it looks like I'll have just enough time to introduce friction, and then I will go ahead and do an Atwood's problem real quick. All right. So we've been drawing boxes and looking at free body diagrams now for several days. And so I have the weight of the box, which is mass times gravity, right? We have the weight of the box and mass times gravity, and we've talked about having a normal force. So there's my normal force if the box is just sitting there. Now, if I have what we call a frictionless surface, and we apply a force to the box, and let's say that force is 10 newtons, we know it's going to actually have an acceleration. So if the box is 5 kilograms and we apply a 10 Newton force, good old F is equal to ma here. My acceleration is going to be F divided by the mass, and that's going to be 10 divided by 5, and that's going to give me, this will be kilograms meters per second squared divided by mass of kilograms. Those cancel, so I've got my 10 divided by 5. This is going to give me 2 meters per second squared, and that's my acceleration. But what we know is if I did this and the surface isn't frictionless, what we know ultimately happens is if I give it a push of 10 kilograms and we send it out there, ultimately it will stop and it won't move. And we can do something really fun and cool. We can say, all right, okay, we can say, all right, we can actually look at this distance. We know we applied a force, and that ultimately ended up so we started, when we applied that force, we end up having a velocity, and then we lose the velocity, and we can know that we have a deceleration. The question is, what is causing this right here to stop? And that's a resistive force. And this resistive force, which in some cases is our friend, in most cases it's not our friend. I couldn't walk if I didn't have some kind of resistive force between my shoe and the floor. I have to have something to push off of in order to be able to walk. Otherwise, nothing's going to happen. But this resistive force is what we call the force due to friction. Okay? That's our force due to friction. And it opposes our push or pull across the way. Now, there's two types of friction. And we all know this because when we're out there and our car is stuck, okay, it stopped dead in the intersection. And we're sitting there and it's dead and we apply a force to it. It takes more force to get it going than it does to keep it going, right? Once we get it going, life's good. Somebody, usually what happens, it takes two of us to get on the back of the car to get it going. And once we finally get it going, one of us can run in, drop it in the car and steer while the other person's pushing. But it took two of us to get it going. Okay. But once I got it going, it's okay. So one is called kinetic friction. And this is the friction that we experience when something is moving. And then static friction is the friction that we have to overcome in order to get it to move. So I can demonstrate static friction really, really well. I got my handy dandy calculator here. I got a slope. Okay, got my calculator on the slope. And I'm going to lift my cardboard. And as long as the angle is such that I haven't overcome static friction, now I've overcome static friction and the and the calculator starts to slide down. But I can actually measure static friction by looking at this angle, okay? I can actually measure that static friction and looking at that angle, and that's actually how you do it. But friction is related to the types of materials. And we know this because if I have a tire, which is rubber, right? Good old tire rubber. If I'm on ice, the friction is going to be very different than if I'm on good old asphalt. So friction is actually dependent upon the material that we have. And friction, we actually define it with a script F. We use a coefficient of friction because we can relate it back to an angle, and we use the Greek letter mu times the normal force, and hence you've all heard that friction is fun because it's a nice mnemonic to remember that that's my friction. This is the force due to friction. This is the normal force. And then there's a coefficient. And the coefficient of static friction, which we usually use as a little sub s, is greater than the coefficient of kinetic friction, which we use a little Greek letter kappa to represent it. And these are related to the materials that are in contact with each other. So leather on ice versus tennis shoe rubber on ice is going to have different coefficient. Yeah.
So in all materials, it's going to be the same. The static is going to have more power than the kinetic.
Static friction is always, rule of thumb is it's always higher. Rule of thumb is it's always higher. I don't want to say it absolute because there's weird things like Bose-Einstein condensates and there's weird stuff where but when we measure it static, it's always harder to overcome static friction than it is kinetic friction. And there's actually a rule of thumb that it's like, one's 2/3 of the other one in general when you're measuring it. So when you guys go to lab this week, which reminds me, when you miss the 5th lab or you get a 0 on the 5th lab, you automatically flunk the course. So you have to make sure that you're getting the labs in, and making sure that you're getting those done. Okay? Because you miss 4 labs, and that's over a quarter of the labs, and that hurts you. So just a reminder there. All right. Hopefully I have enough time to do an Atwood's problem. Okay. So pulleys are everywhere. So we're going to do what's known as an Atwood problem. I've got a mass 1 and I have a mass 2. And they're connected by a string over a pulley. We're going to assume that this is a frictionless pulley because actually this book doesn't introduce friction until the next chapter, but I wanted you to have it for lab because I know some of you have lab tomorrow. Some will have lab Wednesday. Some have lab on Thursday. And speaking of tomorrow, everybody's seen the weather, right? Okay. I actually got up this morning to watch the weather. Because we're supposed to get, depending on where you are in the state of Oklahoma, it can be another slippy, icy mix, which is going to be more towards Oklahoma City. It could be, and depending exactly what time it hits, latest says it hits around noon-ish. It'll be icy. And over here in Tonkawa, it could be 3 to 5 inches. Over in Ponca City, 1 to 3 inches. I didn't quite see what they predicted in Enid. Yeah, it's so tomorrow, and the intent, the way the weather predicted it this morning was that morning's drive is going to be totally fine. It's as the day progresses that it gets ookier. But everybody knows that Saturday, we just had, did anybody see the prediction of that we were going to have a winter storm on Saturday and turn everything icy? It wasn't on any of my apps until about 4 o'clock Saturday, when all of a sudden, oh, by the way, you got a winter storm, we got a winter advisory. Yeah. So tomorrow, just be watching for things. I intend to be here at 8 o'clock for class. But if that's the case, for those of you who have Tuesday lab, we will figure something out. And I don't know what that means for Wednesday, when Wednesday comes into play. So just be aware. If something were to happen for Wednesday, I will probably record a lecture or use a previous lecture for Wednesday. So just kind of keep an eye out. So anyway, friction. We have an Atwood's problem. And when I have something along that's wrapped around, one of the things that we've talked about is if I had a picture hanging or a plant hanging, okay, if I have this and I have the weight of the plant, we have something in here and the string, and there's tension in the string. And if it's static, right, if it's static, the sum of the forces have to equal 0 because that's our first condition of equilibrium. So the tension in the string, the sum of the forces equals 0. The tension in the string minus the weight means that the tension in the string is going to be equal but opposite in direction, the weight of the plant that's hanging on it. So if I'm over here and I look at this and I'm drawing my picture, I'm going to have M1 gravity and I've got tension 1 in the rope. But over here, I've got M2 gravity and I've got tension 2 in the rope. Now, we've all played tug of war, right? Everybody's played tug of war. If I've got a rope between the two of us and we're pulling, I've got somebody pulling this way and I got somebody pulling that way, the tension in the rope is going to be the same throughout the rope. Right? Tension is the same, the tension in the rope is going to be the same. So even though I have this thing over the two sides, as long as it's frictionless, the tension on this side, T1, has got to equal T2. Okay, T1's got to equal T2. So what happens over here is if I have, on this side, I've got M1G, and I've got the other side is the tension, and over here I have M2G, and I've got tension. If M1 and M2 are equal, then this thing would be in equilibrium. But if M1 is greater than M2, we know it's going to go this way, right? That's if M1 is greater than M2, we have it go that way. And we can calculate the acceleration. So let's kind of clean up my page now that we've kind of talked through it and kind of did the diagrams there. Okay, I got 4 minutes. So my Atwood machine here, we've got M2 or M1 and I got M2. So over here now I have tension, I've got Mg, and this is going to be M2, okay? And I have, and we're going to say that M1 is greater than M2 for grins and giggles here. So if this thing moves, so this is M1 times gravity, tension, we end up with an acceleration going down, but this side, the acceleration is going up. But they're attached. So as this one goes down, that one goes up, so the accelerations have to be the same. So now I can get, for around block 1, M1, the sum of the forces is going to be M1 times acceleration is equal to the tension minus M1G. For mass 2, I get the sum of the forces is equal to mass 2 times acceleration. Now this one is going to go down, so I'm going to put a negative in there. Is going to equal the tension minus m2 times gravity. Right now I don't know acceleration and I don't know tension. But I have two independent equations, two equations, two unknowns. So I can go ahead and solve for one. So we can use a math trick, right? We can use a good old math trick. I can add these two things together. How do I want? No, this one I want to do it the other way. So I have m minus m1a is equal to, no, I can do it that way. Okay, we'll do it this way. m12g. And then I've got m1 or m2a is equal to t minus m2g. I'm going to subtract that one from the top one, or the bottom one. So down here I get m1 plus m2a equal to m1 gravity minus m2 gravity, which is equal to m1 minus m2 gravity. So the acceleration is going to be m1 minus m2 gravity divided by m1 plus m2. And once I know acceleration, I can go in and solve for tension. And there are lots of variations on this theme. For example, you can have a table with a pulley. You have a block on the table and are pulling it and have a block here. So you can have a problem that looks like this. You can have a problem, because physicists love doing inclined planes, you can have a problem on an inclined plane. And so we have multiple types of problems that look like this. So that should help you get through the last of the problems in this chapter. We'll do a couple more on Wednesday, and we will start chapter 6 on Wednesday. You guys good over there in Enid? Okie dokie. Hopefully I'll see you, a couple of you in the morning.